So the 5 types of reactions are synthesis, decomposition, single replacement, double replacement, and combustion. I'm going to go through, excuse me, I'm going to go through synthesis and decomposition today because they're basically opposites or reverse. They're reverse of each other. I'm trying to let Pete in here. There we go. So, like I said, 5 types of reactions. So that's the topic for this section, types of reactions. So today I'm going to be doing synthesis, sometimes called composition. We've got decomposition, which is the opposite of synthesis. We have single replacement, sometimes called displacement. They're the same thing. We have double replacement, which I'll talk about next week. And finally, combustion, which is just burning. So those are the 5. I'm going to talk about the first 2 today. So a synthesis or a composition reaction is when 2 or more substances combine to form a new compound. As I go through the 5 types of reactions, I will give you the clues or the hints that you need to identify what kind of reaction it is. The general equation for synthesis is A plus X yields AX. Now, the key to identifying a synthesis reaction is it has one product, right? You're literally combining 2 substances to form one new substance. So if you see one compound on the product side, then you automatically know it is a synthesis reaction. As I go through the different categories of synthesis reaction based on what elements or what compounds are reacting, you'll be able to identify that even without a product on the other side, because there's certain types of compounds that react in a very predictable way. You will have to learn those as well, so that the last half of the lesson today, I'm going to go through a worksheet which has only reactants, and you have to predict what the products will be based on the type of reaction it is. But don't worry, we'll get lots of practice with it anyway. This is probably one of the most important, aside from being able to balance equations and write formulas, identifying reaction type is probably one of the most important skills that you can learn this year. So I did say that there are specific types of reactions that are predictable. And one of those, or 2 of those, I should say, are reactions of elements with oxygen and sulfur. When an element reacts with oxygen, it will form an oxide of the element. And this is why, and I said it last week when I explained how to balance equations, this is why probably the number 1 skill you need in chemistry is to be able to write formulas properly. I did mark the homework, and most of you have like an okay understanding, but I would still like to practice more on that. So I might just give you random worksheets to practice doing that, because without being able to write proper formulas, you're not going to be able to do anything else correctly, including identifying what the products are, writing the formulas for the products, balancing equations, all of that. Like, none of that works if you can't write formulas properly. So in order to be able to identify what the oxide of the element is, you have to understand how to put together elements into a formula. Almost all metals, react with oxygen to form oxides. Why do I say almost all? Because there are some metals that are quite inactive or unreactive, you could say. Later on next week, when I talk about single replacement, there will be a list of elements called the activity series. There's Tigger. There'll be something called the activity series, and I'll give you some hints. It's a long list of about 20 to 25 elements. I don't think it's necessary to memorize that list, because I think that you can use your previous understanding of things I've taught you from before which is also kind of scary because I don't know if you remember that, but it's a comparison of the metals on the periodic table and how reactive they are. So for example, group 1 metals are the most reactive metals on the periodic table because they all have an electron configuration of S1. So everyone in group 1 has 1 electron in their outer shell. And in order to have the configuration of noble gases, they need to just get rid of that 1 electron that makes them extremely reactive. Group 2 all have an S2 configuration. This is all things that I've taught you in the past. An S2 configuration. So again, in order to be stable like the noble gases, they need to get rid of those 2 electrons. So they'll be quite reactive, but not as reactive as if they only have 1 electron. The transition metals are a little bit of a hodgepodge of reactivity. But in general, you can understand that group 1 will be the most reactive, group 2, the second most reactive, and then kind of the other metals follow suit after that. If you're within group 1, they become more reactive as you go down the group. Again, I talked about this in chapter 5 with the periodic law and periodicity. Why elements become more reactive as you go down the group is because the valence electrons are further away from the nucleus. If you look at the periodic table, and we've got periods here, 5, 6, 7. As you go down the group, you are increasing the energy level of the electron in the outer shell. And if you increase the energy level, you're increasing the distance from the nucleus. So 2 things are helping it to become easier to remove the electron. One is it's farther away from the nucleus, so there's less attraction between the negative electron and the positive nucleus. 2, you have many more layers of electrons in the inner shells that are creating what's called electron shielding. Remember, electrons are all negative. They don't like each other. So the more electrons you put between your valence electron and the nucleus, the easier it is to remove that electron. So if I were to ask you between cesium, which is in period 6, and lithium, which is in period 2, which one is more reactive? You should say cesium, because cesium is further down the group. Anyway, I'll talk about that more next week. But all metals except for a few, if I were to ask you what kinds of metals are really expensive, and you should say gold, silver, platinum. Why are they expensive? Because they're quite unreactive, so you can dig them up out of the ground as pure metals, right? You can't dig pure iron out of the ground. You always extract it as something called an ore. So you have iron ore, copper ore, and that's basically compounds that contain iron. And then you have to purify that. So you have to remove the pure iron from the iron ore. Anyway, so when you burn magnesium, you get magnesium oxide. Okay, this is an example of a reaction that is both a synthesis reaction and a combustion reaction. Okay, I'm going to talk about combustion later next week. So here's a magnesium ribbon. Normally I would be in the lab showing you this so that you could actually compare magnesium oxide to magnesium. You know that it is a chemical reaction for 3 reasons. One, there's the release of light. There's also the release of heat, and the substance that you have at the end. This is magnesium oxide. It's quite brittle and it's white compared to the flexible, malleable metal ribbon that you start with. It's obviously a completely different substance. So again, you have to understand writing formulas is one of the most fundamental skills in chemistry, followed by number 2, being able to write a balanced chemical equation with the proper formulas. So if I write out, and this is why before, at the beginning of the chapter, we practice a little bit translating word equations into formula equations, because we basically have oh, that's kind of a bad color, isn't it? Green. Solid, magnesium, metal, burns, to form solid magnesium oxide. Well, that's kind of a strain of my eyeball, those colors too, sorry. Anyway, translating that, you would say MgS plus O2 gas. Why O2? Because oxygen is diatomic. Remember I told you there's H2, N2, O2, and the halogens, fluorine, chlorine, bromine, and iodine. These are the 7 diatomic elements, so they always come in pairs. And they form solid magnesium oxide. So you'd have to work out that magnesium is in group 2, so it has a charge of +2. Oxygen is in group 16, so it has a charge of -2. They're already balanced in a 1-to-1 ratio, so the formula is MgO. This is really, really important. So studying the types of reactions will also help you practice with writing your formulas as well. So we'll go through that. Okay, so this is an example of a synthesis reaction involving a metal and oxygen. They form metal oxides. Now looking at the group 2 elements, they're going to form an oxide with a general formula MO, where M represents the metal and O represents the oxygen, obviously. Why is it MO? Because group 2, they're all have a charge of +2. Oxygen has a charge of -2, so they're formed in a 1-to-1 ratio, which is why the formula is MO. Group 1, on the other hand, group 1 metals have a charge of +1, so they're going to have a formula. This should be a subscript. Sorry, I don't think the font can do subscripts, but it should be M2O, because you're going to need 2 times the group 1 metal to balance with the -2 charge of oxygen. So for example, lithium metal will react with oxygen to form lithium oxide. Again, you have to get the formula correct. Lithium oxide, lithium is +1, oxygen -2, so it's Li2O. Now sulfur is right underneath oxygen, so you're going to have exactly the same pattern with sulfur that you did with oxygen, only if they're going to be called sulfides, obviously. So group 1 and 2 metals are going to react with sulfur to make metal sulfides. Excuse me. Group 1 formula will be M2S. Again, you don't really have to remember this if you understand how to use the periodic table and how to assign charge, how to balance the formula so that the positive and negative charges are equal. Understanding, and this is why it's so important to understand the topic rather than just memorize the procedure, because if you understand the concept behind it, you don't have to memorize anything. You can use your brain. Group 2 metals will have the formula MS, because group 2, of course, is +2, sulfur is -2. Okay, so here's an example. Sulfur, the formula for sulfur, oftentimes it comes as S8, which is why it looks like that. But okay, some metals, usually the transition metals, are going to combine with oxygen to make at least 2 different oxides. This is because the transition metals have variable charge, which a couple of you guys forgot in the formula worksheet, the 6-page one that I gave you over the weekend, because when it came to the transition metals, you forgot to add the Roman number between the metal and the non-metal name to indicate the charge of the transition metal. So if iron can be either +2 or +3, you're going to end up being able to form different oxides depending on whether it's +2 or +3. Same thing with copper. And if you guys have a copy of the periodic table that I gave you, or any copy that shows you the possible charges, then that will help you. So copper can be +1, copper can be +2. So making copper oxide, you could either have copper 1 oxide or copper 2 oxide. when you come to other transition metals like manganese, manganese can be, where is it again? It can be +2, +3, +4, or +7. That means you're going to have 4 possible oxides for manganese. If I give you a question like manganese burns in oxygen to form manganese oxide, I would have to give you which charge it was for you to write the proper formula. If I don't give you the specific charge, like I just say manganese burns in oxygen, then it would be up to you to choose which of the oxidation states it would have. Okay, so iron can be +2 or +3, gives you 2 different oxides. What about nonmetals? Okay, so we covered the metals. Metals react with oxygen to make metal oxides. They can react with sulfur to make metal sulfides. The transition metals are going to make multiple oxides and sulfides because they have variable charge. Nonmetals can also react with oxygen to make oxides as well. Sulfur can react with oxygen to make sulfur dioxide. When carbon is burned, it makes carbon dioxide. So here is the reaction with sulfur. So again, it's the same thing. It's going to form a non-metal oxide. Determining the formula of the non-metal oxide is a bit trickier because they're a non-metal and oxygen is also a non-metal. So it is a molecular compound. It's a covalent compound. So charge doesn't play a part. So that's a bit trickier. We'll get to that a bit later. Hydrogen reacts with oxygen to make dihydrogen monoxide, also known as water. Now, another type of synthesis reaction is with metals and halogens, especially group 1. Group 1 loves to react with group 17 because group 1 wants to get rid of an electron. Group 17 is desperate to gain 1 electron, so it's like a match made in heaven. Most metals react with halogens to make either ionic or covalent bonds. It can be either one. For example, hydrogen gas reacts with chlorine gas to form molecular hydrogen chloride. Let me balance that out. This is not an ionic compound, it is a molecule. Remember, the word molecule implies a covalent bond. Group 1 is going to react with the halogens to form ionic compounds with the formula MX. X represents the halogen, M, of course, the metal. So we have sodium reacting with chlorine to form sodium chloride. I should actually show you. I got a video of that. It's pretty interesting. Very, very exothermic reaction. And potassium reacting with iodine to form potassium iodide. Let me see if I can find that actually. Give me a second. Where's my search bar thingy? Sodium chloride. Movies. Don't want the electrolysis of, do I? Yeah. Documents. I know I have a video. I just can't remember what. Here we go. I can't remember what chapter I use the video for, so I just do a search for here. Search for the movie.
Okay, so I'm going to take out my generating tube. I can see my yellowy flask, and I'm going to take.
So chlorine has this very characteristic kind of yellowy greenish color. He's going to plop a piece of sodium metal down in the, I think that's some kind of clay powder or gravel to help absorb heat. Because like I said, it's an extremely exothermic reaction. The problem is with activation energy, which I haven't talked about yet. I'll do that next year when we study reaction kinetics. But for, I might have mentioned it actually. Was it with you guys or a different class? I can't remember. All reactions require what's called activation energy. And for a lot of reactions, once you supply the activation energy, the energy that's made during the reaction is enough to keep the reaction going. For example, he's going to put the solid sodium into the flask with chlorine gas, but they don't automatically magically just react with each other just because they touch each other. You need to provide activation energy. So what he's going to do is drop a couple of drops of water on top of the sodium. Now, sodium reacts extremely violently with water, so that's going to provide the spark, like the literal spark that will start the reaction.
Take my piece of sodium and I'm going to drop it, hopefully, right in the middle.
Yeah, so you see the sodium metal dropped right here, and it wasn't like this big, huge reaction took place just because the sodium touches the chlorine gas. You need to provide that energy to get it started.
Okay, reposition my camera a little bit. Okay, now.
By the way, I'm looking at this formula. What's that called? Zinc nitrate. And you're missing the 2 over there, but it's on the other side of the bracket. Zinc nitrate.
Let's see if we get a nice little close-up here. What's going on? And refocus. And what we're going to do is I'm going to drop some water on this sodium metal to activate it. And we should see a pretty brilliant reaction once I activate it. So I'm just trying to drop some water with a pipette to start the reaction. And
there's the activation energy needed. And there's the reaction.
there it is. And that white smoke you see is sodium chloride solid. It's a colloid. And so that white smoke is the presence of sodium chloride that we made. And as it dissipates, we'll see where the sodium was, or where the sodium metal was, is now should be a crystal lattice of sodium chloride. Notice the color of the flame was indicative of how sodium metal or sodium electrons get excited and, of course, emit energy. So as this calms down,
one of the things that I'm going to talk about later on are what are called flame tests. There are, like, because we've already talked about how electrons get excited, and when they fall back down to their ground state, they emit photons of energy. There are different elements that have very characteristic colors when they burn. Sodium is orange. And so that's something that I don't generally talk about, and I always want to bring it up when I talk about electron configuration and how they go from excited to ground state, and I always forget. So I will do that next week as well, because I think that comes in handy as well.
okay, we notice this is pretty thick smoke.
Okay, blah, 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 blah. So that's like floating particles of salt. And then here,
so to speak.
So here you can see that's a piece of sodium chloride, and then you can see a couple little chunks here in that.
We're left with an Erlenmeyer flask that's kind of milky white on the outside. That's where the sodium chloride dust has settled. But if you look very carefully, you'll see a white spot. That white spot, and I'll get a close-up in a second, represents where
Yeah, okay, well, we get it. Okay, so there's this, you can see that big chunk of salt there, and a few other pieces where part of the sodium got flung out from the reaction. Anyway, so that is an example of a synthesis reaction between a group 1 metal and a halogen. Okay, is it going to go next? Here we go. Group 2 metals and halogens will react the same way, but of course, group 2 has a charge of +2. So in this case, you're going to have a ratio of 1 to 2 between the metal and the halogen because of the charge. So magnesium reacting with fluorine is going to form magnesium fluoride. Strontium with bromine, strontium bromide. Now, what if we have an oxide that reacts with something else? I mentioned groups 1 and 2 metals. These are called active metals. The oxides of active metals react with water to make metal hydroxide. So this is one of the classes, or like one of the characteristic types of reactions that you'll have to learn. So an active metal, an active metal oxide reacts with water to form metal hydroxide. So for example, calcium oxide, calcium is group 2, so that's an active metal. Reacting with water is going to form calcium hydroxide. So if I were to give you just the first half of that equation, I would expect you, not now, of course, but like in a couple of weeks or so after we practice this a lot, I would expect you to see an active metal oxide plus water, and I would expect you to say, okay, that's a metal hydroxide. Calcium is +2, hydroxide's -1, so the formula is CaOH2. Calcium oxide is also called lime, and calcium hydroxide is an important ingredient in cement. If you've ever had, I think it's called Antacid or Eno, these are something called antacids. Generally, you take them when you have a stomach ache because they are made of the active ingredient calcium hydroxide. You can see that here. Now, hydroxides are alkaline, and you take them, like the name says, antacid, when you have an upset stomach, is because your stomach is producing too much acid. You have hydrochloric acid in your stomach. And so if you take these tablets and you chew them up, or you dissolve Eno in some water, and it creates an alkaline solution. When you drink that, it helps to neutralize that excess acid in your stomach. Now, non-metal oxides are going to react with water to make oxyacids. And this reminds me of teaching you how to name acids, because I completely forgot, which is why on that naming homework, the very last section, which was all about acids, I gave you all of that for free. So I have a general rule. This is not in relation to how the acid is formed. It's only a trick to remember how to name the acid. Now, the trick that I use is something called itis-adic. And that rule basically says that if you can isolate, like I isolate here, this ion, even though it doesn't come from the ion, you're not combining sulfite with hydrogen to make sulfurous acid, but it is, like I said, it's a shortcut, a trick. So if you isolate what would be the polyatomic ion without the hydrogen, you get SO3. And of course, that's -2. The name of SO3 is sulfite. Okay. So the name of the acid, when you add hydrogen, is sulfurous acid, itis, right? If the polyatomic ion ends with ITE, the name of the acid is going to be OUS. If I take H2SO4, and if I isolate SO4 as an ion, it's called sulfate 8, which means, the acid is called sulfuric acid, adic. So itis-adic is the trick that I use to name oxyacids. If you isolate the part of the formula from the acid without the hydrogen, what's the name of that as an ion? Then you can translate the name of the acid. That, again, is not a reflection of how oxyacids are formed, because they are not formed by adding hydrogen to sulfite. It's not an ionic compound. It is a molecule. So Oxyacids are formed when nonmetal oxides react with water. Oh, sorry, I just got a message. So in this case, you have sulfur dioxide gas, which is a byproduct of the combustion of fossil fuels, by the way. Actually, no, sulfur trioxide and sulfur dioxide, both. Basically, pollutants from combustion of fuels. And it reacts with water in the atmosphere and it forms acid. In this case, it would be sulfuric acid with SO3. And that's where acid rain comes from. You also have nitric and nitrous acid that are made from nitrogen monoxide, nitrogen dioxide. But all of these are byproducts of using fossil fuels. Yeah, so that's what I was just talking about. An air polluted with sulfur dioxide reacts with the oxygen in the air to form sulfuric acid. So not only are you forming sulfurous acid, but then sulfurous acid is also reacting with the oxygen in the air to form sulfuric acid, and this is the cause of acid rain. Okay, I'm going to skip the practice problems for now because I want to make sure I cover decomposition reactions because they are literally the opposite, and there's a couple more categories in this section. So decomposition is literally the reverse of synthesis. So where synthesis is A plus X yields AX, the general equation for decomposition is AX decomposes to A plus X. So again, I told you there would be a clue for each type of reaction. This one is probably the easiest one because you have only one reactant. If you have only one reactant and a chemical reaction takes place, there's only one possibility in that it breaks down. That's decomposition. A lot of times there is a need for some kind of energy to make this happen, either through light or heat. The simplest kind of decomposition is binary compounds. So for example, when you pass electricity through water, you're going to break or separate the hydrogen from the oxygen gas. The interesting thing about this, if we were actually at school and we could do this in the lab, you could actually see that because of the balanced equation, you would physically see twice as much gas being produced as the other gas because you use electrodes, right? Because hydrogen has a positive charge, this is going to be attracted to the anode, which is negative, and the oxygen will be attracted to the cathode, which is positive because oxygen is a negative ion. So at the anode, you would see twice as much gas being produced as the cathode because of that balanced equation. This process is called electrolysis. Again, lysis means to break, and electro, obviously, electricity. I think I mentioned, oh God, way in the beginning, probably one of the first lessons ever, I mentioned hydrolysis reactions and how you break down large molecules like proteins into amino acids. This means to break with water. Okay, and that's an example of hydrolysis. These are the electrodes that I was talking about. The oxides of less active metals, which are in the lower center of the periodic table, decompose into their elements when heated. For example, mercury oxide will decompose to mercury and oxygen, like that. Okay, one of the other categories that I didn't talk about in synthesis, but also applies, metal carbonates break down to make metal oxide and carbon dioxide, which means metal oxide plus CO2 is going to create a metal carbonate. Okay, that is another class of reactions that you can remember. They go in reverse, so you don't have to remember both the forward and the backward, just remember one. So I can actually make a list of the synthesis reactions or decomp reactions. I can do both and send it to you so that you can remember. You don't have to remember both lists because they're literally reverse of each other. So if you remember one, you can remember the other. So in this example, calcium carbonate, remember the triangle on top of the arrow means heat is applied, and calcium carbonate decomposes to calcium oxide plus carbon dioxide. Again, if I say metal carbonate breaks down to metal oxide and carbon dioxide, you have to be able to write the correct formula for the metal oxide so that you can balance the equation properly. And like I said, don't worry, we're going to do tons of practice, especially with these two groups, because these are the two hardest ones, in my opinion. All except for group 1 metals decompose when heated to make metal oxides and water. Now, this makes sense when I said that metal oxide plus water makes metal hydroxide. We just did that in the reverse, right? Metal oxide plus water makes metal hydroxide. Now we're just going in reverse. So if you see calcium hydroxide and you see an arrow with a delta, that means heat is being applied. You have only one reactant, which means it's decomposition. Then you look at the type of compound it is. It's a metal hydroxide. It will decompose to a metal oxide and water. I'm definitely not going to get to that worksheet today, I think. The last one, the last category is with metal chlorates. When metal chlorates decompose, they make metal chloride and oxygen, which means, I just lost my Bluetooth connection. Awesome. All right, which means metal chloride, I could spell, maybe, plus oxygen yields metal chlorate. Again, it's all two sides of the same coin. So here we have potassium chlorate. Again, we're decomposing. We have only one reactant and we have the delta sign. So metal chlorate decomposes to metal chloride. Again, you have to be able to write the formula properly, and oxygen. So if I have KCl plus O2, then you think to yourself, okay, that is synthesis and it's a metal chloride plus oxygen, metal chlorate. What is the formula? Actually, before that, what is the formula for potassium chlorate? Potassium is K plus, chlorate is ClO3 minus 1, so it's a 1-to-1 ratio, KClO3. And I don't care at the moment whether you know which state that will be. We'll deal with that later. You should be able to, by now, have oxygen as a gas for sure. Now, if we make oxyacids by reacting nonmetal oxides in water, then the decomposition of oxyacids are going to produce nonmetal oxides in water. So this is a nonmetal oxide. Sorry, this is this is an acid. How do I know? Because it's a nonmetal oxide with hydrogen and it's aqueous. This is the big key right here. So that's going to decompose into a nonmetal oxide plus water. Another example, you've got H2SO4. So you've got that. They don't form by polyatomic ions, but as soon as I see these formulas, I see hydrogen with a polyatomic ion. That's just how I see it. So we've got polyatomic ion with hydrogen that's aqueous. That's an oxyacid. Oxyacids decompose into nonmetal oxide plus water. All right. I know that was a whole lot. I've only got 5 minutes, but I would like to do, I'll also do by cable. I would like to just go through a couple of things. Let me get out of here. Since we're going into break anyway. Yeah, I want to share with the cable. Oh wait, was that sharing? It's irritating. Yeah, share. Can I do it?